All right, let me try another video solution after a question here. Let's see, it's number 25 here from chapter 15. And let me read it here. It looks like there's three parts, an A, B, and a C. It says, but a simple pendulum has a mass of 0.25 kilograms, a length of 1 meter. It's displaced through an angle of 15 degrees and released. What is A, the maximum speed, B, the maximum angular acceleration, C, the maximum restoring force. And then it says, solve this problem by using the simple harmonic motion model for the motion of a pendulum, and then also solve it using the more general principles. So this would be like your Physics 121, conservation of energy. So maybe a picture is worth drawing, and so here is a vertical line on a ceiling. You pull it off to one side. Let's see, the mass was 0.25 kilograms, and you let it go, and it swings back in and forth. And so there is this angle of 15 degrees when you let it go. Now, the first question, A, says its maximum speed. And so using the idea of this chapter with harmonic motion, omega A would be the maximum speed. So the A would be the amplitude when you pull this 15 degrees, and so it would be this arc length S. So maybe I'll just put amplitude equals arc length S, and that would equal to r theta. Now that's a formula for getting an arc length in radians. So the length of it, I believe, is 1 meter. Let's come back to a simple pendulum, mass of and length of 1 meter. Yeah, so the radius is 1 meter along this rotational arc. And the angle, and they're going to go 15 degrees, but let me convert that into radians. All right, so here's my amplitude. So amplitude is 15 times pi divided by 180. And so we're looking at an amplitude of about 0.262 meters. Okay. Now, the period of the pendulum we solved. We also solved for omega. So I've memorized it in terms of the period. It's L over G. But we also know the period is 2 pi over omega, so that means omega is G over L, square root of G over L. Okay, so to get the omega, I could also then take my calculator and go 9.8 divided by 1. And the square roots of all of that would be a 3.13 radians per second. All right, so the maximum speed, omega A, so omega is 3.13, and A is the 0.262. And so we'll just multiply them together. So I'll just hit times, and then I'll go up to the length. I think that was the length, right? 2.6, yeah, hit enter. And hit enter on that. And I guess we're looking at a maximum speed of and I'll just call it 82 meters per second. And again, that's using the simple harmonic motion approach. Now, the more general principle would be, hey, we could have done the same thing, and we did back when we did Physics 121. We did something that looked like this. We pulled it off to the side. We said let it drop, and using conservation of energy, this would be its change in height, if you will. Maybe I'll call that its initial height. So when we apply conservation of energy, initial energy equals final energy, we would have mgy initial and no kinetic. And then as it swings down to here, it would have no potential and all kinetic. The m's would cancel off, and so if you take the 2, the g, the y initial, take the square root of that, you would get v. Now, y initial is going to take a little bit of geometry, because we know this is 1 meter, and then of course we would know this is 1 meter times the cosine of 15 degrees. And this whole thing then is 1 meter. So we know that 1 meter equals this y initial and the 1 plus cosine of 15 degrees. So y initial would be this 1 minus 1 cosine 15 degrees. Okay, so I better check my mode because I bet I'm in radian because I've been doing most of the stuff with those formulas on simple harmonic motion. Okay, so let me go back to degrees and then go cosine of 15 degrees. Go 1 minus that number, and we're looking at a height of 0.03407 for that initial height. So if I'll take that initial height and multiply it by 9.8, multiply that by 2, and then take the square root, I get a speed of 0.82 meters per second. Not a surprise. It's the same thing when we thought of it as simple harmonic motion. So, of course, it's based on the same forces and energy. So if all you want to know was the speed at the bottom, I'm not sure I would have thought of it as a simple harmonic motion. I would have just thought of it as conservation of energy. And I think that's, the author's point. We could look at it either way. And he does this through all 3 steps. So moving on to B, it says, what is the maximum angular acceleration? Okay, so the acceleration, the maximum anyways, using simple harmonic motion was this omega squared A. Now those we solved earlier back here on page 1. I should have labeled it. But there's the A, and there's the omega. So 3.13 squared, and the A is 0.262. And that would be the maximum acceleration, not the angular acceleration, but the acceleration. So 3.13 squared times 0.262, and we're looking at a maximum acceleration of 2.57 meters per second squared. And then remembering that angular acceleration is the translational acceleration divided by the radius, which in this case is the length of the pendulum, which in this case is 1, is then going to be 2.57. And when you divide by 1 meter, at least the meter will cancel, and you would just write it as radians per second squared. And so, solve this, let's see, what is the maximum angular acceleration? Okay, good. Now, if you were doing this by I'll call it the fundamental methods, if you will, I guess I would do maybe a torque here. I'd say, all right, let's calculate the torque and divide it by the moments of inertia, and that would give me my angular acceleration. Of course, it would only give me at that point, so I guess I need to then realize that as this thing swings out, so there's the force of gravity, mg, there's the distance away, and so when I go to calculate a torque is r, f, and sine of the angle between r and f. And so coming back to the picture, this is the r, okay, and there's the f, so this is the angle between them, and that's the same as the swinging angle. So I'll just call it theta. There's no point in having 2 different angles here. I was kind of worried about maybe the swing angle and the angle between R and F would be different, but they seem to be the same. And then the moment of inertia, as it sticks out here, would be just a single object, so it would be m, and we would call this then an r squared. And of course, you can kind of see in this problem that you're going to get its maximum at the maximum angle. Okay, so when this is up here. All right, so that's going to be our 15 degrees. Hopefully you can also see that the calculation for torque is the distance away, which is actually an L for the length of the string. And for that matter, that's also where the mass is, so this is also an L squared. So one of the L's up there would cancel off. So we would be left with the force, and in this case it would be the force of gravity, so that's an mg, and then the sine of 15 degrees, all divided by the m, and only one of the L's canceled, so we still got 1 meter. And then, of course, the F would cancel. The M would cancel. And so we're going to have a G, we're going to have a sine of 15 degrees, and then we're going to divide it by its length. So 9.8 meters per second squared. I'll put the length in, which is only 1 meter, so numerically doesn't change anything, but it makes the units right. And then sine of 15 degrees. So putting my calculator here, I guess I would have the 9.8, the sine of the maximum angle of 15 degrees, and gives me a 2.54 radians per second squared, and I'll chalk up the difference there between some rounding, and they agree with each other. Okay. And then, I guess I'll call this page 3. And part C is kind of this same basic idea. Let me figure out where it was here. What did it say? The maximum restoring force. Let's see. I guess the first thing that comes to my mind is not the oscillation motion. The oscillation motion doesn't really have a force in here. So I'm not real sure if there is a way to do this with oscillatorial motion. Let's see, the maximum restoring force. Because in both cases, I guess maybe just how we got to the A, when we did the simple harmonic motion stuff and got to maximum A, we would then have the mass, 0.25 kilograms, and I'd multiply it by the maximum acceleration, which is 2.57. But to be honest, they both come to mind, and I don't see a way of doing it with simple harmonic motion. It's just the standard way of MA. I suppose the only difference, though, would be how we got to the A, because we got to the A a little different. But they're both just mass times acceleration. In this case, 0.25 times 2.57, and we get 0.6425 newtons. 0.6425, well, maybe this will be a little different. 0.25 times 2.54, it would be 635 newtons. Yeah, so I don't know if that one follows the same pattern. Maybe I should flip over here to the solution. Yeah, and that's how they did it both times. So, good. They seem to match. So again, just kind of an exercise on oscillatorial motion, but to show you really it's based in the fundamental physics of mechanics that you learned back in 121. Hope that helps.